Welcome to the Correggio Academy session on renewable energy. This session will explain how solar PV, wind energy and battery storage are central to the EU Green Deal, not only for achieving European climate neutrality by 2050, but also as a strategic driver of industrial competitiveness and economic growth in a decarbonized European economy. This session will be a window into the beautiful world of renewable energy. So please be welcome. My name is Lucian Indries. I am from Romania and I've been with Correggio Consulting since 2020, having worked on many technical assistance and consulting projects in various European countries. I am also a CorreggioNET officer, which means that I work on our flagship product, which is called CorreggioNET, and it's our regulatory compliance service for wholesale market participants. CorreggioNET system has existed for over 10 years and it keeps expanding both in terms of both geographical scope as well as in terms of content. My specific area of expertise is EU and national energy legislation and regulations, and I have hands-on experience in international technical assistance projects as well as in consulting projects in the EU and also in some energy community member states. I'm also very passionate about renewable energy projects and have always been, and also about sustainability. And I have, for instance, been part of teams that have performed technical due diligence on many gigawatts of renewable projects. This is both wind and solar in Europe and especially in Romania. At the heart of the boom in renewables that we see today, and that will be the subject of our Academy session today, is the so-called EU Green Deal, which requires an introduction. This is the European Union's flagship strategy to achieve climate neutrality by 2050 and also to cut greenhouse gas emissions by 55% by 2030 compared to 1990 levels. At the heart of this transition of the Green Deal is the massive deployment of renewable energy sources, particularly solar photovoltaic and wind energy, which are now and have been for some time the most cost-effective and scalable clean energy technologies available. However, their intermittent nature makes battery energy storage systems best essential to integrate more renewables by balancing supply and demand. So together, PV, wind and battery storage form the backbone of the clean energy transition. And we are currently seeing a boom in this deployment, and this is the subject of our Correggio Academy today. So the agenda for today's Academy: first section will be about solar PV developments. Second will be about developments of wind projects. And finally, we will be discussing BESS, battery energy storage systems, which are crucial in bringing these two together. What is actually solar energy? Well, some say solar energy is actually nothing else but nuclear energy from a safe distance. The sun's energy is produced by nuclear fusion reactions in its core, which release vast amounts of energy in the form of light and heat, which we capture here on Earth as solar energy using what we call solar panels. So solar power on Earth is actually a passive consequence of distant fusion, nuclear reactions, nuclear power produced by our sun at a distance of approximately 150 million kilometers away and protected by the vacuum of space which lies between the sun and our Earth. Moving on to the global horizontal irradiation, the best areas on the planet for solar PV are generally those with high solar irradiance, as seen in this map, generally around the equator, also with clear skies and low cloud cover, with cooler ambient temperatures ideally, because this helps improve solar panel efficiency, and also the land needs to be flat and unshaded. However, it's important to note that even though, for instance, areas around the equator, as in north of Africa, for instance, or the Arabian Peninsula, these areas have also observed very high temperatures which reduce solar panel efficiency. While deserts offer exceptional solar irradiance, the high ambient and surface temperatures can reduce panel output, especially during the peak midday heat. For every 1 degree Celsius rise above 25 degrees Celsius, most solar panels lose about 0.4 to 0.5% of their power output, which can be significant in some instances. Moving on to PV cells, PV modules, strings, and arrays. So everybody has seen solar panels, and this is how they are colloquially called, solar panels, but the technical term is actually a photovoltaic module. In this presentation, we will be referring to photovoltaic modules as PV modules. So the cell, a PV cell, is the smallest element in a PV module, which produces electricity through the photovoltaic effect. By the way, the photovoltaic effect was the only Nobel Prize received by Albert Einstein in 1921 for his discovery of the law on the photovoltaic effect, which was itself a pivotal contribution to quantum mechanics. So PV cells are arranged in PV modules, as seen in the diagram, which we colloquially named PV panels. But the term solar panels is actually misleading because these panels use the photovoltaic effect, so they should be called PV panels rather than solar panels. So modules are connected in series to create a string. The name comes from the fact that they are connected in series, and strings are connected in parallel to create an array. We have, therefore, the basics of building a PV power plant. But there is more. There are different types of PV modules. So PV modules themselves are of many different types, and the science and the physics behind them, as well as the manufacturing technology, is very complex, with important advancements in efficiency, reliability, and most importantly, cost reduction over the last 20 years. There are several types of differentiations. So first of all, you have P-type versus N-type solar panels, which refers to the base semiconductor doping that is used in the silicon wafer. Therefore, the P and the N stand for positive and negative, so positive type and negative type cells. Today, older P-type technologies are slowly being phased out in favor of N-type, higher efficiency modules, which are more costly to produce, but the price has come down in the recent years. You have also a differentiation between monocrystalline and polycrystalline, and also flexible or thin film solar cells. So monocrystalline solar panels are more widely used and are generally considered to be superior to polycrystalline panels in terms of efficiency and performance, with higher efficiency rates often exceeding 20% compared to polycrystalline panels, which usually range between 15 to 17% efficiency. And of course, you have the thin film PV cells, which have the advantage of being flexible and can be used in a variety of interesting applications. A new development is what are called bifacial panels. So these are essentially two-sided panels, and as you can see in the picture, they let the sun shine through. So monofacial panels are the old types of panels that everyone is familiar with, which absorb sunlight only on the front side. These are commonly used in rooftop and small-scale installations due to their lower cost and simpler setup. As mentioned, a relatively new invention are bifacial panels, which are basically cells sandwiched between two panes of glass. They have a glass surface both on the front and on the back, and can generate electricity from both the front and the rear sides, thereby increasing total energy yield. This is especially important in ground-mounted PV systems, where the modules can benefit from the albedo, i.e. the reflectivity of the surface. This is the technical term, albedo. For instance, grass reflects about 20 to 25% of incoming light, whereas desert sand reflects approximately 30 to 45% of incoming light through the albedo effect. Of course, snow reflects even more light. While monofacial modules are still more widely used in residential settings, bifacial, so these glass-backed modules, are rapidly gaining ground in utility scale for their superior performance and durability. Yes, they are more expensive, but the cost is recouped through the higher efficiency and durability of bifacial solar panels. These are particularly effective in desert climates. Moving on to the mounting structure. You have, of course, rooftop installations. Everybody is familiar with these, and the rooftop installations are actually very practical and very efficient on big industrial warehouses where such an installation presents multiple advantages. First of all, it's an excellent use of space. I mean, you already have the roof, you don't have to use any land, any ground surface that would otherwise be used for agriculture. There is no complex permitting needed, except of course for the grid permitting to the electricity network. You don't need to go through the process of changing the land use, for instance. There is no digging necessary for the DC cables. You have reduced costs with the mounting structure as well. So for instance, there is no need to ram profiles to install complex mounting structures because you use the rooftop as the base for the installation. And rooftop installations also have the advantage that the energy produced, or part thereof, can be consumed on site, therefore reducing the strain or the load on the electricity grid, allowing for more PV installations nationwide. There is also an interesting distinction between fixed tilt and solar tracking PV panels. So what's the difference between these? As it can be seen in the picture, fixed tilt PV systems mount the solar panels, the modules, at a constant angle and are simpler, cheaper, and require less maintenance. However, they produce less energy than the tracking systems because these systems, as they are fixed, do not follow the sun's movement. So in the northern hemispheres, the PV panels face true south to maximize exposure to sunlight throughout the day. This means that they capture the sun's arc as it travels from east to west, slightly skewed towards the southern sky. Whereas in the southern hemisphere, it's different. PV panels on fixed installations always face true north for the same reason, in order to follow the sun's path across the sky. However, a better solution than fixed mounting installations for PV panels are what are called trackers, solar trackers. These are essentially man-made mechanical sunflowers. Solar trackers, what they do is they adjust the panel orientation throughout the day to follow the sun's path across the sky. There are multiple types of solar trackers, such as single-axis trackers, which rotate east to west and typically increase energy yield by 15 to 30%. And there are also more complex dual-axis trackers that follow both the horizontal and the vertical angles, maximizing output, especially in high irradiance locations. So this is an important distinction that has to be noted, the difference between fixed tilt and solar trackers. Of course, fixed tilt is always cheaper to install as opposed to solar tracking, which requires a more complex mounting structure with electric engines, as you see in the picture, for the tilting mechanism. But over time, solar trackers can recoup the cost of the additional investment compared to fixed tilt installations. Talking about installations, how are solar panels actually installed on site? Well, this is the unseen part of solar PV installations. Of course, the modules are the most visible part. Everyone has seen a solar PV park, for instance, driving along on the highway. But there is a lot of work that actually goes on behind the scenes to install these PV modules. So the installation of the ground-mounted structure, as you have seen in the previous picture, is done by a process that's called ramming. You see the picture of the ram there. It has nothing to do with actual rams. It's the name of the machine, as you can see in the picture on the left, that drives steel posts or steel piles into the ground to create essentially the mounting structure, which is then further installed by screws. So in the left you see a pile driving machine, and on the right you see a big trench. Well, that big trench is necessary for the installation of the DC cables. As you can see, the trench is actually quite wide because it collects all the cables from all the strings where the PV modules will be installed. And this cable leads all the way to the inverter where the DC electricity, so direct current that's being produced by the solar panels, will be transformed into AC, or alternating current, which is actually the type of electricity that is currently used in the grid and that is of most use for all of us. But as you can see, there is actually a lot of digging that goes on when constructing a solar photovoltaic power plant. And this is often unseen, but it's important to take note that there is a significant amount of digging and ramming that's going on. And then there is, of course, a lot of installation. Large PV installations in the orders of tens of megawatts can have hundreds of thousands of individual PV modules that are installed on the structure, be it fixed tilt or with solar trackers. So that's a lot of panels to be installed, a lot of modules, a lot of ramming, a lot of cables, and a lot of combiner boxes for the cables to be installed, a lot of screws to be tightened, a lot of screws to be checked. These are often the overlooked parts of any PV installation, but these works are actually what makes solar energy possible today, and in fact so cheap, because solar energy is probably the cheapest form of energy today. In the next picture, you can see the process of installation of PV modules on the structure. So on the left, you see the box with the PV modules that are delivered on site. You see the mounting structure. In this case, it's a fixed structure that has been already installed. So you see the vertical piles that have been driven into the ground. You see the structure that has been mounted with screws awaiting installation of the modules. You also see on the right, of course, the areas where the modules have already been installed. And in the center, you also see some ends of cables. These are the cables of the individual strings. You don't see the trenches because here the cables have already been installed and only the PV modules need to be attached to the fixed structure. But this is a good indication of the progress and of the procedure, technical procedure for installing PV modules. It's a lightweight construction. It's one that can be quite easily removed at the end of the lifetime of the PV installation. However, it's important to note that there is still actually quite a lot of work that goes on for installing these PV modules. And as you can see, if the power plant occupies many hectares and it's in the order of megawatts, then there is actually a lot of work that goes on to create this. And as an order of, just to get an idea about how much land you need for how much power, roughly today you would need around 1 hectare of land for 1 megawatt of installed capacity. It can be even less than 1 hectare for 1 megawatt, but in the past, more than 1 hectare was necessary to install 1 megawatt of solar power because of the lower productivity, the lower capacity of the individual solar PV modules themselves. The power of the modules has increased quite significantly in the past 20 years. So we have panels today that are 600, 700 watts per panel, even more. And these panels have led to a very high increase in the productivity per hectare of solar PV installations, which means that less land is needed to install them, or for the same surface of land, more power will be produced. Of course, we have been talking that PV panels are producing DC electricity, so direct current, of course, through the photovoltaic effect that we have explained at the beginning, was essentially discovered by Albert Einstein. but we have to do something with that DC electricity. We have to transform it into AC electricity, and that's done using inverters. This is the technical term for the devices that transform DC electricity into AC electricity. So you have in PV installations two primary types of inverters. These are central type. So in the picture on the left, you see that fridge or wardrobe looking device. That's a central type inverter. And you also have string type inverters. These are smaller and are attached to each string, as you see here in the picture. So central inverters are large, high capacity inverters that are typically used in utility scale PV projects. What they do is they aggregate the DC electricity from many solar panel strings and connect it to AC power at a central locations. These central type inverters are designed to handle hundreds of kilowatts to even megawatts of capacity in a single unit. They are cost effective at scale, they are efficient, and they are also easier to integrate into high voltage transformers and substations. On construction sites of solar power plants, solar PV power plants, they are usually delivered in what are called skids, which is essentially a metal plate that has the inverter, and alongside with other equipment such as transformers, switchgear, protection systems, and offering cooling, especially for areas where the temperature gets very high, which together form a plug and play solution for a utility scale PV project. So central type inverters offer economies of scale as well as speed, standardization, and durability. So through their delivery as skids in these installations that are essentially trucked in, which contain the transformers, the inverter, and everything, you save a lot of time and effort in creating a solar power plant. On the other hand, you have a different philosophy, which is to use string inverters, and as opposed to central type inverters, of which you have a few large ones. String inverters are usually small. They're relatively small boxes, as you see in the picture, and they connect to solar panels arranged in strings to convert the DC electricity that the PV modules generate into alternating current for use or grid injection. So the difference is that string inverters are also cost effective and more simple to maintain, but the problem is that they perform best when all the panels in the string receive uniform sunlight, as shading on one or parts of the panels and of the modules in the string can reduce output for the entire string, and this can lead to imbalances in the power plant. What's also important to note is that you have more complicated cabling that has to be done if you install string inverters, because of course you have to install one at the end of each string. But of course there are different philosophies. There is no good or bad option. Many PV projects choose central type inverters, other PV projects choose string type inverters. They're all good. There is no clear advantage to either of them. So the recommendation is to use whatever is available and whatever is preferred by the designer that you choose for your solar PV power plant. Now, of course, every project needs a development track, and here is where it actually gets a bit more boring, because of course everyone likes to see the end result. But the permitting part, the boring part, is the one that no one really wants to deal with. But of course, that's necessary. It has to be done. So the development is a key part of any PV project in order for it to reach the so-called ready-to-build stage. So in order to reach a ready-to-build stage, you have to follow the following steps, which are, of course, the first project is to secure the land. This can be done by outright buying the land, or what can be done is obtaining an easement right, such as, for instance, what is called a superficies agreement, for an easement for a contract essentially to rent the surface area of the land, but not all the land, just the surface of it, in order to build the PV facility on the surface of that land. And this is possible because PV parks are lightweight constructions which can easily be removed at the end of their lifetime. So for instance, as opposed to buildings which need a solid concrete base, oftentimes PV installations do not need any sort of foundation. Of course, there are exceptions to this, but usually ramming of the profiles into the ground ensures sufficient stability. So that's why easement contracts are usually preferred, because at the end of the easement period, essentially the renting of the surface of the land, it's possible to dismantle the product and return the land essentially in the condition that it was originally found before the PV installation was installed. Moving on, the second aspect that needs to be performed is the zoning approval. So this means approval from the municipal or regional authorities in the regional or local zoning plan. This is of course not a problem, for instance, in desert areas, for instance, where you have ample spaces which usually are not used and there are no neighbors. So the zoning is actually much more easy to do in desert areas, as opposed to, for instance, populated or busy areas in Europe. Europe is quite a dense continent, so oftentimes it's a bit difficult to find areas that are suitable for PV installations. And of course, the land needs to be secured. This is also, for instance, not a problem with regards to securing of the land in desert areas, which, as mentioned, because they are not exactly used very intensely, then the price for renting that land, for using that land to install a solar PV facility is significantly lower. For instance, in Europe, where land is more expensive, actually the cost of using the land, of signing the easement, can actually be quite significant in some instances. And another aspect which can actually lead to quite significant costs for the PV installation is the need, which you have at least in some countries, to perform what's called a land use change. So for instance, if you are planning to install a PV facility on agricultural land, this is of course allowed, depending on the category, the quality category of the soil, but it's generally allowed to install PV panels on agricultural land that's being used for active agriculture. However, this needs to be done following a specific procedure for changing of that land use, which generally involves payment of a fee. So for instance, in many countries, you have to pay a fee per square meter or per acre or per hectare of land that's being removed from the agricultural circuit, so from agricultural land use. And the land use will be changed, at least temporarily, to mixed, so photovoltaic, solar production, and agriculture, or fully for PV energy production with no agriculture. If a project combines agriculture and electricity production, this is called an agrivoltaic project, and these present very interesting advantages, and we see many more of these being installed in Europe. But in general, agrivoltaic projects are more rare than pure projects that are created for electricity production on a given surface, because then if you only produce electricity, it's possible to use that space more densely, especially if you use solar trackers to install the solar modules. Another important step, maybe the most critical step, is after performing the land use change and the zoning approval, and of course securing the land, is to obtain all the necessary permits. So these are usually obtained from the local authorities. Of course, this may vary from country to country, but it's generally the local or regional authorities that offer these permits in the planning permission stage. And of course, after all these permits are issued, it's important to go to the next step, which should not be overlooked, which is securing the grid connection. Actually, this can be the bottleneck because in many parts of Europe the grid is congested. So that means that availability of the grid for grid connection of new generation capacities, be they renewable or non-renewable, is limited. This means that it's important to start this process early to perform the grid connection agreement. So this means reaching out to the regional DSO, so the distribution system operator for electricity, or in case of larger projects, it's necessary to talk to the TSO, to the transmission system operator, for obtaining the right to connect to the grid. In many countries, auctions are being performed in order to secure the necessary capacity to connect the project to the grid. In other countries, there are no auctions. It's based on a first come, first serve basis. So you can just go to the TSO, apply, and then get into the pipeline of projects and get an order number for your project to be connected to the grid. Whereas, as mentioned, in other countries, you actually have to pay for this grid connection. So you have to compete with others, and of course, the highest bidders will win and will have the right to connect to the grid. This is probably the most critical part of any project, especially today and in the future from now, because there is an abundance of projects, but not all of them have grid connection rights. So it's important to always check this element, whether a grid connection permit, whether a grid connection agreement or GCA is signed, and what are the conditions of that contract, and when is the planned grid connection date. Another key aspect that needs to be taken into account is the environmental aspect. So you have to have an environmental impact assessment, an EIA, or an environmental and social impact assessment, an ESIA. And these are often necessary, especially required by international financial institutions, which may be looking to finance such renewable energy projects. Well, depending on the size and location of the project, it may be necessary to perform a full-scale environmental impact assessment to include biodiversity, visual or noise assessments. Whereas in other more remote areas, it may be sufficient to only perform a simple environmental impact assessment. For instance, if you're planning to build a project on agricultural land that's far away from inhabited areas, that's far away from any environmentally protected areas, and in that case, usually a simple environmental impact assessment will be sufficient. Of course, after all these documents are obtained, so the permits, the grid connection agreement, the environmental impact assessment is prepared, the final step is obtaining the construction permit. And once the construction permit is obtained, or the building authorization as it's called in other countries, in some parts of Europe, the project can be considered ready to build, which means that physical works can start. And these are of course based on detailed engineering drawings, and they have to comply with building codes and all the national restrictions regarding construction works, which oftentimes also include solar PV installations. Finally, you need an electrical installation and operational license in order to connect that facility to the grid. This is required in most jurisdictions. Also required would be certification of the design of the facility and also the grid compliance of the equipment used. And here especially compliance need to be checked for the inverters that you are planning to use. So if, for instance, you are planning to use a type of inverter that has not been used in a particular country, this can usually be checked. TSOs have lists of approved inverters. And if your planned inverter type is not on that list of that particular TSO in the country where you are planning to install your PV facility, it's important to check with the TSO beforehand whether they approve the particular inverter type that you are planning to use, in order not to get into a bottleneck, because there are of course many different types of inverters, of manufacturers, and of technologies that are being used, and not all TSOs accept all types of inverters. Finally, the last step in the project development track is of course the commissioning and the final acceptance after the construction period has been completed and the plant is finally built, or the modules are installed, the inverters and the transformers are in place, and the grid connection installation is performed. You have to perform tests, operational tests with the regional DSO or TSO, depending on how large the power plant is, and various inspections and approvals are needed before commercial operation can start. And commercial operation is defined by COD date, so another key date that all renewable energy projects have is so called the COD date, so the commencement of operations date, which means the end of the commissioning period, when the power plant has all the approvals necessary to be a full-time participant to the market as a power producer. And from that moment on, the process is completed and the power plant can be sold as operational, for instance. Moving on to the next section on PV modules and inverters, it's also important to note that today 97% of all the PV module imports into the European Union, in Europe, come mostly from China. China is by far the leading country in terms of production of PV modules. They have a plethora of companies that produce PV modules of all the different types. You have Huawei, Sungrow, so on and so forth. And also in the inverter space, you have a lot of companies that dominate this market generally. And in Europe, on the inverter market, it's only around 75% of the inverters being installed that are coming from China, but this is still a significant number. And what I wanted to mention is that, of course, it's clear that China dominates the global production of PV modules and inverters, not only with regards to exports to Europe, but globally. But the European Commission, so the European Union, has launched what's called the European Solar Charter Program. This was launched in 2024 to bolster the EU's PV manufacturing sector. And this charter emphasizes the need to reduce dependency on imports and to strengthen domestic PV manufacturing industry, which is key for ensuring that the EU is self-sustainable also in this respect. And this initiative aims to support the competitiveness of European PV manufacturers and to promote high-quality, sustainable products that are made in the EU. And for instance, in the inverter space, there are some manufacturers that produce excellent quality inverters for PV installations, and these can also be exported by the EU into other markets. Moving on to the next section, which is on wind energy. Of course, everyone has also seen wind turbines. I personally find them fascinating and very, very beautiful. And a question actually comes: if solar energy, we called nuclear energy from a safe distance, is wind energy also a form of nuclear energy from a safe distance? Well, the answer is, to a certain extent, yes. Not fully, not like solar energy, but at least to a certain extent, wind energy is also nuclear energy from a safe distance. Why and how? So the sun heats the earth, but it heats it unevenly, because of course the earth rotates, and that causes air pressure differences in the atmosphere. And these pressure differences create the wind patterns as air moves from high pressure to low pressure zones in the Earth's atmosphere. And so of course the heating of the atmosphere, the differentiated heating, is caused by the sun directly, and that's why wind energy is also, in a way, indirectly a form of nuclear energy from a safe distance. But as differently from solar energy purely, there is also the Coriolis effect, which has an effect on wind power. The Coriolis effect, from the geography lessons, is caused by the rotation of the Earth, therefore also shaping global wind patterns. And in the picture you can see the effect of the Coriolis effect on the atmosphere. So in the northern hemisphere you have air, so the winds, which are deflected towards the right by the spinning, the movement of the Earth. And in the southern hemisphere, the winds, the air is deflected towards the left by the rotation of the Earth. So wind turbines capture that kinetic energy of the moving air and convert it to electricity. So both solar and wind energy are ultimately powered by our sun. So in case of solar PV, it's direct nuclear energy from a safe distance. And in case of wind power, it's indirectly nuclear energy from a safe distance by the sun's heating effect on the Earth, plus the effect of the rotation of the Earth. So it's all solar energy, sun energy. Moving on to the map with the wind resources, so the wind potential of Europe in this case. This is a map of wind resources at 100 meters of height, because that's typically the height of wind turbines. So it's important to look at the wind resource at this height where wind turbines operate. It's clear to see that the highest wind potential in Europe is especially in Northern Europe and in coastal regions, where there are consistent and high average wind speeds, often exceeding 7 to 9 meters per second, which make both onshore and offshore development economically attractive. So countries bordering the North Sea, such as UK, Denmark, and the Netherlands, have some of the highest technical and economic wind speed potentials, which with large-scale offshore zones already contributing significant shares to national and therefore to EU electricity generation. Central and Eastern Europe also hold significant potential for wind energy, especially in countries such as Poland, Romania, Baltic states. Ukraine also has good potential, where policy framework and grid updates help unlock viable onshore sites. In Southern Europe, including parts of Spain, Greece, and Italy, you also have solid potential, but only in specific mountainous or hilly areas or in coastal corridors, because you have here a more variable wind profile, which requires a more detailed site assessment in order to establish whether wind energy is actually feasible or economically feasible in that location. And of course, you always also have that not in my backyard phenomenon. So of course, wind turbines are huge, and sometimes people don't want them in their backyards, the so-called NIMBY effect, not in my backyard. And this can also be a factor that affects whether wind turbines can actually be installed in a potential location or not. For instance, locations with high touristic potential may not be ideal for the installation of wind turbines because, for instance, for some at least, they may be considered an eyesore. For me, at least, they are wonderful. They are beautiful wonders of engineering and a product of humanity, as pyramids were in their day. Today we have man-made machines such as these huge wind turbines. But of course, you can't put wind turbines everywhere. You still have to have clear sites, for instance, in beautiful seaside areas. So that's why wind turbines are not installed everywhere, but usually in areas, or if they're installed offshore, they are at a distance where generally they cannot be seen from the beaches or from the shore. So wind turbines have actually evolved tremendously over the last 10 to 20 years. So in the early 2000s, onshore wind turbines were typically 1.5 to 2 megawatts per turbine. And usually the hub height was generally between 60 and 80 meters. The rotor diameter being around 60 to 80 meters generally, but by the 2010s, so 10 years later, advancements in materials and blade design have pushed onshore turbines to 3 to 4 megawatts per turbine. Most of the installed turbines are actually in this range, 2 to 4 megawatts that are operational in Europe today. But the turbines that are being produced and installed today are actually much larger, again due to advancements in material design and blade technology. You have onshore turbines that today are in the range of 5 to 6 megawatts per turbine, with hub heights ranging between 80 to 150 meters, and the rotor diameters of 100 to 170 meters. So that means that the length of a single blade, as seen here in this beautiful picture, for an onshore turbine would be over 80 meters long. And of course, this is in itself a major engineering achievement to make such a long piece of equipment that has to withstand the elements for 20, 30, 35 years, which is the lifetime of a wind power plant. You can see how long these are when they are transported on land by truck. Usually roads have to be completely closed to allow their passage, and also they require special land transportation equipment and complex procedures with road closures and such. So as mentioned, wind turbines are getting bigger. How big actually? Well, they're getting so big that you can actually compare them with buildings that you may know very well. So for instance, offshore turbines are easily larger than the rotor diameter and the height as well, easily larger than the London Eye. And some offshore wind turbines are actually as large as the Eiffel Tower, as you can see here in the picture. Why is this? So for instance, offshore wind projects have larger turbines because they have higher installation and maintenance costs. So it makes economic sense to install fewer but bigger and more powerful turbines to maximize output. So this would be output per turbine, which means per foundation, per cable, and per service strip of the vessels. So you want to minimize these as possible, and that's why the turbines have to be as big as possible offshore. So 10-15 years ago, you had offshore turbines that ranged in 6 to 8 megawatts. However, since the 2020s and the last 5 years, we've seen essentially what it is, a race to create the largest offshore wind turbines. This is a race generally between European and non-European, Chinese, American manufacturers, with the largest turbines easily exceeding 12-15 megawatts per turbine today. So you have leading models such as from GE or Siemens or Chinese manufacturers that can have tip heights of the turbine that can get close to 300 meters. 300 meters is the height of the Eiffel Tower. So actually the picture that I'm showing here is of an older type of turbine, which is almost as big as the Eiffel Tower, but not as big. But turbines of today are as big as the Tour Eiffel, which of course, when it was completed in late 19th century, it was the tallest building on the planet and was a sight to behold. And today we have wind turbines which actually move and generate electricity and are of the same height. And as you can see, their height actually also competes with other famous landmarks, such as the Chrysler Building in New York City, which was again the tallest building on the planet for a short period of time in the 20th century. So the technological progress is enormous. And also, as a comparison, it's important to compare that the swept area of the rotor of one of these large offshore turbines is larger than 6 football fields. So the area that's covered by the rotor, by the blades in their rotation. Every rotation covers 6 football fields, which is of course an enormous area, an enormous amount of wind that they catch. So this large size of new turbines for both onshore and offshore makes them much more efficient, much better at capturing the wind, and therefore much better at producing electricity. So the larger the rotor, the more efficient the turbines. They can also work at lower wind speeds, and also the lower the installation costs, because you have fewer turbines to install to reach the same electrical capacity. So for instance, 15 years ago or 20 years ago, you would need 3 times as many turbines compared to turbines of today to install the same power generation capacities. Wind turbine generators are also of different types. There are 2 main types in terms of operation. Of course, all the secrets go, and the power generation goes in the tiny box on top of the wind turbine, which is called the nacelle. And in the nacelle, you have all the business end, essentially. You have two different types. The first type is gearbox-based turbines, which use a mechanical gearbox to increase the low rotational speed of the rotor, which is 10, 15, 20, 25 RPM, to a much higher speed that's suitable for electricity generation, which is 1500 RPM in the generator. This is the most common configuration of wind turbines, especially for onshore turbines. And gearboxes allow for smaller and lighter generators, but the downside is that they add complexity and weight in the maintenance that needs to be performed due to the presence of moving parts, which of course can be subject to wear. So you have to do your oil change on your wind turbine from time to time. On the other side, you have on the right side, you see a direct drive type wind turbine, which connects the blades directly to the generator, which eliminates the gearbox by using a low speed and high torque generator that's connected directly to the rotor. This reduces mechanical losses, improves reliability, and minimizes maintenance, which is especially important for offshore turbines, where access is limited and very costly, because of course it's done by vessel. So every time you need to do even an inspection, you have to send a vessel all the way to the turbine, as opposed to some guys with a vehicle. So direct drive systems are heavier, they're much more expensive upfront to build, but they're increasingly favored in the large offshore machines that you find produced by, for instance, General Electric or Siemens Gamesa or Chinese manufacturers, and for their long-term durability and efficiency. In terms of wind turbines manufacturers, it's important to note that as of 2025, the most important manufacturers in the world are the ones that you see on the screen. So you have Vestas from Denmark, you have Siemens Gamesa from Germany and Spain, you have Nordex from Germany, General Electric from the US, and of course many manufacturers from China, such as Goldwind, Mingyang, so on and so forth, which are also producing wind turbines of big sizes and producing a significant number of wind turbines as well. It's important to note that European manufacturers are leaders in this field, so the most technologically advanced turbines, so to say the best ones, are made in Europe. Also, the blades are constructed in Europe. For instance, there are many factories for blades in Denmark. So Europe is very much focused in offshore innovation, for instance. And these producers, the European producers, are especially strong with their sales in Europe. Chinese manufacturers mostly focus on the internal Chinese market, which is enormous. It's the largest energy market in the world, actually. And you have, of course, GE from the US, which also produces top-tier models, both for onshore and offshore models. And all these manufacturers compete on capacity, rotor size, so essentially blade length, technological innovation like direct drive, as mentioned, and of course sales. Who sells more to where? The final slide on wind power is about capacity factor, and that's also very important to mention, because capacity factor is the way to measure how much electricity a power plant actually produces, in this case a wind power plant, compared to how much it could produce if it ran at full power all the time. Of course, wind and solar are intermittent, so for instance, there is no sunshine at night, and similarly there are days when there is no wind. Fortunately, it would be lovely if there would be wind every day, constantly, as the power sector would have a much easier time to cope with wind power, and wind power could ensure all the energy needs of the world. But unfortunately, this is not the case. So we have to look at capacity factor. And capacity factor for wind turbines in Europe generally ranges from 25 to 35%, depending on the location, turbine technology, the wind resource, of course, the turbine age. You have turbines which are already in operation for close to 20 years or even more than 20 years. But then again, you also have coastal areas or in the north of Europe, such as Denmark, the UK and Ireland, which often achieve capacity factors that surpass 35%, which is excellent, thanks to stronger and more consistent wind speed conditions. In comparison, Southern Europe or more continental Europe usually sees lower values, so lower capacity factors due to more variable wind speeds, more complex terrain, and in fact, newer turbines, so technological improvements and turbine designs that lead to taller towers, so the higher hub height and larger rotors, larger blades, have actually steadily led to increased capacity factors for wind turbines installed in central continental Europe as well, because these larger turbines and more modern ones are able to capture more wind. Offshore turbines have much higher capacity factors usually than onshore ones, which is why there is actually a rush to install these where possible and where economically feasible. Capacity factors onshore usually range between 40 and 55%, with some modern installations in optimal North Sea locations even reaching capacity factors of 60% or more, which is great. And this is due to the strong and consistent and constant wind speeds that you find offshore. The large size and the advanced technology of offshore wind turbines, including direct drive and taller towers, have also contributed to these very high capacity factors that we have seen in the offshore space. Finally, the last aspect that I want to mention about wind power, and that's important, is the parameters that usually turbines that are quite similar between all turbine models, which are the cut-in speed and the cut-out speed. So of course, if the wind is too low, so usually generally lower than 3.5 meters per second, turbines don't really spin, so then they don't produce much power. As soon as the wind is higher than 3.5 meters per second, turbines start spinning slowly at first, and they start producing electricity. And you see the power curve here as the wind speed increases. As of wind speeds that are higher than 6, 7, 8, 10 meters per second, or higher, 15 and higher wind speeds, turbines produce at rated power, so at the full capacity, especially the large ones today that can operate at lower wind speeds as well. But it's important to note that all wind turbines have a cutout speed. So if the wind gets too strong, like hurricane force or gale force winds, then the wind turbines have to stop. And usually this cutout speed is around 25 meters per second. This equates to very strong wind speeds, and the wind turbines have to stop and are stopped in order to protect themselves from damage from the very strong wind speeds that are higher than 25 meters per second. Moving on to the section on battery electricity storage systems, or BESS. So grid-scale battery energy storage systems are large installations that store electricity and discharge it to support the power grid. They help balance supply and demand and stabilize frequency. So battery energy storage systems, or BESS as they are colloquially called, play a critical role in Europe's energy transition, particularly as the continent rapidly expands its deployment of intermittent renewable energy sources like wind and solar. For this, BESS is a key enabler that helps integrate the variable renewable energy sources like solar and wind into the grid. So in the picture on the right that you see is a grid-scale lithium-ion battery manufactured and deployed by Prime Batteries, which is a Romanian company which has received EU funding and support over the past years. This was done through the European Institute of Innovation and Technology, or EIT, the Inno Energy Fund. So this collaboration, this EU-supported project aims to scale up this particular company's annual production of batteries in the EU all the way to 8 gigawatt hours, which is a tremendous capacity, positioning it as a significant contributor to the European battery value chain with gigawatt hours level of annual production of batteries. This is, for comparison purposes, this is akin to the Tesla Gigafactory as they use in their marketing in the US or in China. So battery factories at the gigawatt hour level. And there are several such battery plants at gigawatt hour level that are being planned in the EU. And the one I mentioned is just one of them, which is fairly advanced because it's already producing and installing batteries. The one that you see in the right-hand picture is a battery that was installed last year, and it's quite a significant one. So this is just one of several examples of EU initiatives for supporting battery energy storage for grid applications. It's also important to highlight that the EU has implemented the so-called EU Battery Alliance, and the scope of this alliance is to develop a competitive battery value chain in the EU. And there is also batteries regulation that will ensure the sustainable battery production, recycling practices, focusing on long-term sustainability of the battery business. Estimates for needs for BESS installation in the EU only range between an investment need of 4 to 5 billion euros per year, every year in the coming years until at least 2030. And this is necessary in order to support the installation of more and more intermittent renewables. And by the way, besides the support that the EU provides, many member states of the European Union have also launched national ambitious programs for BESS deployment with different subsidies and incentive schemes in order to accelerate the deployment of BESS. So why are battery energy storage systems so critical today? Why do we see a boom in them, and why is everyone talking about them? Well, of course, as mentioned, the problem with renewables is that while clean and abundant, they are intermittent, so they generate electricity variably. Solar, of course, only generates when there is ample sun, and generates very little when the conditions are not ideal, when it's very cloudy or where there are thunderstorms or in winter. The same with wind. Sometimes there is no wind, so there is no electricity generation, and this creates significant challenges for grid stability and reliability. So BESS, battery energy storage systems, address this problem, for instance, for solar photovoltaics, by providing the possibility to do what's called time shifting. So to store excess electricity that's generated during periods of high renewable output, such as, for instance, the midday production of PV power plants, and discharge it during periods of lower production, but of high demand and also high price, by the way, such as evenings. So this also not only creates an advantage for the grid by time shifting, so by shifting the generation, storing the generation during midday and releasing it during the evening, but it also creates, due to the price difference between the time period during the middle of the day when prices of electricity are very, very low and solar production is very high, and prices can even go negative, and evening periods when prices of electricity are the highest during the 24 intervals, the 24 hours of a day. So this also creates a business opportunity to do price arbitrage between between different time intervals. So the time intervals when you may even be paid to charge your battery if electricity price is negative, as we have seen on several instances, even during weekdays. So you charge your battery and you get paid to charge your battery, and then you sell the power in the evening at much higher price and therefore capitalize on this price difference. So BESS help balance supply and demand in real time. They help to reduce curtailment of renewables in certain instances, And of course, they minimize reliance on fossil fuel backed up power, for instance, for ancillary services, for TSOs. And as mentioned, they also create business opportunities for this price arbitrage. Additionally, BESS or battery electricity storage systems can provide ancillary services to the grid, to TSOs, such as frequency regulation, voltage control. So for instance, you have AFRR and MFRR that batteries can qualify to provide to TSOs. So there is yet another possible revenue streams for battery storage owners and operators, separately from just purely doing price arbitrage on the market. For instance, on the day ahead or intraday market, there is also this possibility to provide ancillary services and be remunerated, for instance, for the capacity that you make available to the TSO for AFRR, for instance. So it's a business case that's becoming more and more interesting in Europe today. So batteries are essential for a resilient, flexible, and decarbonized European power grid. That this has become clear in the past years. Another advantage is that they can also help with black start capabilities if, God forbid, such an event happens, as we actually have seen in Spain in late April, which was a major event for the European continental grid. Batteries can also help with this, which helps TSOs tremendously. For instance, by allowing certain parts of the grid to be restarted from to have black start capability without conventional power plants. And this is actually a key capability that's very much welcomed by grid operators. And not to mention that also another advantage of battery storage systems is that in congested grids, they help to defer or to even avoid costly infrastructure upgrades, such as by for instance increasing the capacity of lines, by building more lines and to strengthen the electricity grid. The fact that you have battery storage systems distributed across a national system can help by shaving peaks and mitigating such instances of grid congestion, and can lead to a much better and smoother operation of the grid with efficiency for all the grid users, of course. And this is again a major advantage. In terms of BESS deployment in Europe, over the past 2 years, we have seen an incredible boom in BESS installations and deployment. And this, of course, as mentioned, is fueled by Europe's rapid push to decarbonize its power grid. And only in 2023, which is not so far back in time, we have seen BESS installations reaching more than 17 gigawatt hours, which is twice as much as it was in 2022, for instance, and marks a doubling of the capacity that's installed every year. And we have seen this trend also in 2024, and expectation is for the same to happen in 2025 with a marked increase of installed capacity. And of course, this is all this rapid extension of BESS deployment is fueled by the need to stabilize the grid amidst increasing share of intermittent renewables like wind and solar, which in many countries comprise a significant portion of the installed capacity, especially of the new installed capacity. And of course, as we see a lot of the old fossil fueled generators being phased out, like coal and coal power producers, and being replaced with intermittent solar PV and wind capacities. Therefore, the need for BESS is increasing. As with wind turbines and solar PV panels, advancements in battery technologies have been tremendous over the past years, which has led to a decrease in cost. And there are also supportive policies, as mentioned, in Europe, but also in other parts of the world that have supported and propelled the adoption of BESS. And Europe, for instance, is planning to increase its capacity, as mentioned, by many times the current capacity by the end of this decade. So estimates are that installed capacity should be increasing exponentially over the next years, which provides very interesting business opportunities. Of course, as with solar PV equipment, most of these BESS capacities that are deployed in Europe today, but for that matter in other parts of the world as well, are built and imported mostly from China, which is by far the leading country in the world in terms of battery production and battery value chain. But as mentioned in previous slides, the EU is also working hard to create a domestic BESS ecosystem, as mentioned, at least for certain parts of it, which will create value here in Europe. So to conclude and to wrap up this academy session that has covered solar PV and wind on the generation side of renewables and battery storage as the means to help integrate these intermittent renewables into the grid. The transition to renewable sources is of course key to the EU and will remain so, and it's the main driver for reaching climate neutrality by 2050 as assumed by the EU, and cut emissions by 55% by 2030, or get as close as possible to this very ambitious target. So clearly the EU must continue to accelerate the deployment of solar PV, of wind and of BESS, because they work together very well. And of course the financials are also very interesting with the price of these technologies dropping significantly in the last years, and also in the midst of the gas crisis in Europe that has hit over the last years, sending gas prices through the roof, and also increased ETS prices for fossil-based generation. In this context, the deployment of renewables plus storage plus BESS is looking increasingly interesting as a business opportunity for developers, for companies and for traders. But this clean energy transition should not only be seen as a business opportunity from a trading, from an operation perspective, but also as an industrial opportunity for the EU to develop. So to reclaim Europe's industrial competitiveness. This was key, and it's a business opportunity which the EU should capitalize. So as mentioned, the Green Deal, it's not actually solely an environmental agenda as it's sometimes touted in the press, but it's actually a much broader growth strategy from the EU, which includes strengthening the EU's industrial competitiveness. We have seen this in the Draghi report, which was published with very interesting conclusions. So in this context, the rapid expansion of renewables globally, not only in Europe, represents an economic opportunity for Europe, a generational one, in fact, because this is the power generation technology of the future. And Europe should seek to lead in this role rather than follow or import, as it's mostly the case today. So by scaling up domestic manufacturing of PV modules, high quality and very sustainable ones, also propping up the inverter business in Europe, supporting the wind turbine industry in Europe, which is leading. European producers are amongst the leading producers worldwide in wind technology, and also creating a value chain and an industrial, a competitive industrial ecosystem for battery energy storage systems in Europe, which would replace the imports from Asia. This is a major economic opportunity for the EU, and not only it will create hundreds of thousands and hundreds of thousands of skilled jobs and generate high value exports, which would bring value added to the EU economy, it will also reduce the EU's strategic dependency, for instance, on imported fossil fuels, of which EU is probably one of the areas of the world which is most dependent on fossil fuels imported, like LNG or pipeline gas, so on and so forth. Renewables, of course, hit the earth indiscriminately, and it's an opportunity that the EU should just catch and capitalize in order to make its energy system more clean, but also to develop and capitalize on this major business opportunity. So as mentioned, to conclude, the Green Deal, besides tools like the Net Zero Industry Act, the European Solar Charter, which were mentioned in this presentation, also the European Battery Alliance, they all explicitly support this major EU reindustrialization effort, which we hope will be as successful as possible. And these new technologies, solar PV, wind, and BESS, are not only enablers of decarbonization, but they are the pillars of a new, competitive, and innovation-driven European economy, which will hopefully see the EU becoming the leader in global green energy. Because this is a very, very interesting field, and it's what the future will hold for all of the world, not only for Europe, despite maybe some backstepping that we have seen. Clean energy, the advantages of clean energy are clear in terms of price, ease of deployment, and the future has to be green, no question about that. It's already in economics, so the economics support it. So it's quite clear that this is the direction that the whole planet will go into. Maybe not as fast as originally imagined, but it's definitely the direction that should be taken and that we are taking. And other parts of the world will follow, will support. Also, the EU will work together with the EU, and we will see major deployment of renewables plus battery storage systems in other parts of the world. And actually, we are seeing this quite significantly. So the EU is, as mentioned, is not necessarily the lead importer of such technologies, but also other parts of the world are significantly scaling up their capacities because it makes economic sense. And if it's good business and if it's good for the planet, then it's good for everyone. So thank you very much. We would like you to get in touch with us for full description of all our services. We'll be very glad to be in touch with you and to provide insights into our standard service offerings and also more tailored consulting services that we can offer. So thank you very much.